Okay, this is phase two for our project proposal for automated irrigation by Hunter Reed, Grayson Moore, Cannon Kittner, and Colin Heisel. In this slideshow, we're going to review the project. We're going to show the design sketches that we made, which includes the gates on the pipe and the actual workings of each individual gate. We'll also go over the basic design needs of the project, including power and handling water pressure and connectivity in the system. And we're also going over design analysis and how the functionality of the gate will operate within the pipe in the system. And finish with the conclusion.
Hey, my name's Colin. I'm going to be going over the project review and our new sketches. So the project that we're working on is trying to automate the opening and closing of these gates as shown on the left. Farmers spend countless hours every morning, at least the farmers that I worked for. It's about 6 hours every morning for two guys to go to every single field, right? They just kind of divide and conquer opening and closing these gates every morning, and they'll spend about 6 hours every morning just moving water on these gates. So I think it would save a lot of money if you could cut those 6 hours out of the morning and find a way to automate this where they don't have to go to the field every day. And here's our old photo on the right before I get to our new sketches. Just super simple, right? Just an actuator to pull and close these gates. And I think the biggest challenge really is going to be trying to get this on a network where they wouldn't have to even come to the field. And I'll go more into the physics of how these pipes actually work, so it makes a little bit more sense on the next slide. Okay, so here's our little diagram that we drew up. So you have a water source coming from the left side, and the thing you need to know about irrigation, unless it's a pivot, like those giant things that go in circles, they have their own wells in the ground, but these are ran off irrigation coming from the county. Uh, Water is never perfectly distributed. There's thousands of farms, thousands of fields that are all trying to pull water off the system, and there's people who regulate who gets what time, and there's all a schedule for it. So you never get like a perfect amount of water. So that's kind of like where these gates come into play. So you can imagine there's hundreds of yards of these gated pipe, down a whole field. And eventually, when that water comes in for the week or whatever, it comes to this end cap, and like the reason the end cap is to build pressure back up those 100 yards. And the reason that these gates have to be closed and open certain days and certain times is if you had all these gates open, or there's just holes in these pipe to distribute the water, you would never have enough pressure to evenly get it to every single gate. And these pipes are going up and down hills, and you have to build your own pressure. So you can only open 10 to 20, and the way you kind of decide that is there's these things called, or at least we call them, overfills, and it's basically just a break in the pipe randomly. Really, it doesn't really matter where you put it. It would just be, I don't know, like where you think, I guess, the most pressure might build up. So the whole point of an overfill is when this water builds up, if you don't open enough of these gates and the pressure gets too high in this pipe, you can just blow these gates off, or you could crack the poly pipe and it'll just explode, and I mean you're gonna flood your entire field. So the point of the overfill is just to make it an open system. So if the pressure ever gets so high that I can push water all the way up this and just come out of the top, it's just a think about it like a rectangular just plastic bin that has an open top, really simple. It's meant to be a low pressure system, but obviously you get 300 yards of water being rushed into a pipe, it can build quite a bit of pressure. So you're hoping that before these gates just explode off, that water would overfill over the top. And usually you're out there, watching and opening these gates, and you should see water, start overfilling if you don't have either enough gates open, or the gates you do have open, they're not open enough. So in future drawings, I guess, or maybe like a design that we're still working on, is maybe you could just put sensors inside the pipe so that if no one's there, obviously, and they don't see this overfilling, they're not going to know to go open more pipes, or to tell a system to open more gates in the pipe. So maybe we could put a sensor inside the pipe, and I think the perfect range is like 7 to 10 psi. These pipes are rated for 25 psi, and that's really pushing it. If it went over 25, it would probably just explode this pipe. But our design, you can see these little clamps right here. So usually it's just these open gates like that photo in the last slide, but we're hoping that we can put these little actuators on top of each gate and make it where the farmer doesn't have to come out here and just slowly tap each of these open. He can just tell the system to, move the next 10 gates and open it 25% of the 100% gate, like the range of 100%. So that's our goal. And then the next slide we can go into the actual design. All right, so here's our little sketch of our mechanical device. Super simple, just a motor, a piston, actuator, and a piston, and a closed-off body just to try to help it from the weather. I think these things are, I wouldn't call it really tough, but it can sit there in the sun. It won't ever hurt it, but it won't hurt to just have a little plastic box around the motor and the piston and let the gate get pulled into the actual box. And you're never going to open these things 100%. I mean, I know it shows it right here, but it doesn't like if you have it open 100%, you're only going to open right, maybe 10 max, because you do want a good amount of pressure shoving that water out. So if you open them up 100%, you're only going to open maybe 5 to 10, and it's not very efficient for when you're trying to water an entire field. But it actually gives us somewhere to put solar panels on top of the actual case if we do put a box on top of it to protect it. And we're trying to keep it as simple as possible because things go wrong 24/7 and you don't want to have to try to fix a complicated system. So if we just made our own device that we would be selling or just putting on all these pipes, if anything goes wrong, you can just pull that box apart and it would be super simple, right? Just something to connect the actual piston to the gate. Probably just in the next photo, our example is just a screw and a nut. Just drill a hole through the gate, you just attach it in, super simple. The piston and the motor, and then just one little solar panel on the top that obviously would just be screwed onto the top of this box, and it would be sealed off. But super simple to pull apart. It's kind of like the name of the game. Just keep it simple. If they ever have to fix it, really easy to pull it apart. So here's the closer up sketch, I guess. So like I said, bolt and a nut just on that gate. And inside the box, it would probably be cut off about right here. You would just have your piston connect to it, pulling and pushing that back and forth, and your motor to do so. Just super simple. When we make this into a network, I think we should just figure out what 100% is when that gate is open and just make it a percentage, right? So the farmers don't have to think of opening it, an extra eighth of an inch or anything. It's just whatever percent of 100 that you want to open or close it. And I bet by the first day of using it, you would know your happy medium of what percent you want to open these gates at.
For our basic design needs, power is the most important thing for our gate, and solar power is probably going to be the most effective design strategy for our gate. So for solar panels, we did some research and they produce 8 to 10 watts per hour per square foot of solar panel. That's under ideal conditions with sun out, perfect temp, all that stuff. And 8 to 10 watts per hour per square foot is equal to 0.06 to 0.07 watts per hour per square inch. So we use that with our device requirement of 0.21 to 0.42 watts per hour. That requirement comes from the device's ability to move the gate, open and close, but also connect to all the other gates in the system and be able to be connected to an app or some sort of network that they're all intertwined with. So with that 0.21 to 0.42 watts per hour needed, that would require around a 3 to 7 square inches of solar panel per gate. So that's actually realistic because it will be able to fit right on top of the gate, and that's where each one's power will come from, and that way they can come individually without any long wires attaching all the different gates.
Another one of these basic design needs is water pressure. So if all the gates are open, there won't be enough water pressure to properly irrigate all the different rows. You have to have at least some of them closed so that the water can get all the way through the pipe and reach out far enough across these rows to properly water all these crops. But if you have too much, it goes all the way to the end of these standpipes. There's also fall pits, they call them. So water will pool up, and in these specific standpipes, it'll shoot up. And so the farmer can see from across the farm if there's too much water pressure, and that's just how they know to turn it down. Our design allows the farmer to make individual adjustments so that they can control from a distance. If there's too much water pressure, they can bring it down, and it also just makes it easier to set and have it consistent so you don't have to change it all the time, and it can change automatically. And looking at design analysis, materials are going to be super important because our product needs to be able to withstand the weather, it needs to be able to withstand water pressure, temperature, just all these things. So it's going to be either made of PVC or 316 stainless steel, and PVC is a lot more accessible, it's going to be cheaper, but 316 is a lot stronger. So the internal parts are probably going to be made of 316, and if there's an outside part that could be made of PVC in maybe a warmer climate with a lot less severe weather, we could do that. But for the important parts, we're going to have it out of 316.
Our next part of the design analysis is the functional components, which is essentially just the logistical parts of our system, how everything fits together, how it's going to work, how it's going to be powered. The first part of this section is the actuator. The actuator is the main part of our device. It has a motor and a piston, and that's how we're going to open and close the gate. The actuator will be powered by a solar panel, which sits on top of the body of our system, and our actuator sits inside of the body. The actuator consists of a motor and a piston. So the solar panel will power the motor, might charge a battery so that the power can be tapped in from at any time of day. But the motor will be powered by the solar panel, and then the motor of an actuator makes it spin. The motor, spin something. That's how it works. And we need to move linearly, the piston to move back and forth. And so, to be able to do this, you can't do this through spinning. So the actuator, the motor is attached to a screw, which when spun will push it forward or backwards, just as if you were screwing something into a wall. If you screw it one way, it goes forward. If you screw it the other way, it comes back. The screw will be attached to the piston, and so that way the piston can go back and forth depending on how you command the motor, which way you command it to spin. The next part is the piston will be attached to the gate, which we need to open and close. And the end of the piston will have a little gap in it, as can be seen in the picture here. And that gap we will slide the gate into. And you can bolt through it, and we'll have a washer and nut on the other side. That just ensures that the gate stays firmly connected to our piston. And so whenever we spin that motor and push the piston back and forth, that will push our gate back and forth however we want it to. Our final part of the design analysis and functional components is just the body and the solar panel. The body will be really simple. It'll just be a sort of casing to house the actuator, all the parts in there, and also the gate when it's retracted or even extended a little bit. The motor will be inside of it, the piston, which these two parts make up the actuator, and the gate will also be inside of there. As I said, whenever it's spun back and the gate is open, the gate will be protected from any weather or anything like that. It'll be under this plastic build. The body will be made out of PVC, I said on the previous slide, and just very simple, very cheap. It's just a good casing to keep all our stuff protected from the weather. And the gate will just slide through a gap in one side of the body. The rest of the body will just be enclosed. It'll be only that one opening. And the back of the body will have a little slot where the hose clamp will go through to wrap around the pipe. And that's how all of our devices are connected to our irrigation pipes. And the last part is the solar panel. The solar panel will just sit on top of the body, and that'll give us plenty of room to get as much solar panel as we needed, which, as Grayson talked about previously, was 3 to 7 square inches of solar panel. And we can fit that easily on top of this. And we can even cover the whole thing almost in solar panel, just to ensure that we have plenty of power. And since the motor will be inside of the body, the solar panel will easily connect through the top of the body and straight to the motor. And the basics, it'll just be a basic solar panel build, just like any other solar panel you'll see. Maybe one on a garden light or even on some calculators. Very simple, very easy to power, very sustainable. Yeah.
Thanks for watching this phase of the design and modeling of our project.